Okay. So let's hook this thing up, and we'll start programming. There we go, MATLAB. There it is. Let me first rescale things because I make these fit a little bit better. Okay, so actually, you know what we're going to do? We're going to start off from where we were a little bit yesterday, which is, first of all, we're going to think about, yesterday was working here with a domain of size L here. I'm going to make this a little bigger. Think of a time domain, a time span of, call this capital T. So I'm going to look at my signal in time over 30 whatever. It could be 30 seconds. It could be 30 milliseconds. Whatever the units are. Who cares? We're not really going to work with units right now. And I'm going to chop that signal up into 512 points. This is my sampling rate. So over 30 seconds, I'm going to sample 512 times, for instance. And then I chop up my time. It goes from negative t over 2 to t over 2. And in n plus 1 points, as we talked about this yesterday, which is when you think about this, you say, I'm going to take my domain. I'm going to use Fourier transforms here. So I'm going to think about, I'm going to use the Fourier transforms, periodic. So the last point is the first point. So that's why I need n plus 1 points. It puts in the last point. But really, I don't care about the last point because it's the same as the first. So what I do is I shave it off right there. I just take the first 1 through n points. Okay. We'll bring stuff in as we need it. Now, big important move right there. This tells me the actual frequency components. When I break this thing up into 512 frequency components, that's what I'm going to do. I first have, the FFT thinks I'm going to be working on a 2 pi periodic domain. I'm not working on a 2 pi periodic domain. I'm working on a domain of size 30. Okay? So size 30, but I have to then rescale because the FFT I'm going to call on thinks 2 pi. So that's why you have the 2 pi over t there. So you get the 2 pi over t, and then all these integers right here, okay? All those integers are actually now sort of frequency components. Cosine 0t, cosine 1t, cosine 2t, right? So that 0, 1, 2 gives me the frequency, okay? So we're going to think about taking this signal in time and decomposing it into frequency content. Now, remember in the radar problem, I send out a burst of acoustic waves, or if I'm thinking about the radar problem, I'm sending out electromagnetic energy at some frequency, omega naught. I know my frequency I want. Okay? And normally what you do in this, whatever your center frequency of interest is, you sort of normalize so that you say, I'm going to look at frequencies that are away from omega naught. Okay? So omega naught will be my 0 frequency. Okay. So now let's take a simple example. And what I want to do is just take a function. And what we're going to do is Fourier transform it and look at it. Okay, so for instance, I could take, and now let's kill the rest of this here. Here's my signal. My favorite function. Okay, there it is. And let's just plot it, t versus u, so we can admire this simple little function, which is just a bump. Granted, that's not that fancy. But there we go. Suppose I think about my signal in time, and this is it. So this is negative 15. So you think about your time, from time negative 15 to time 15, and this is what happens. You go along, you get this bump of a wave that comes through. Okay? And what we want to look at then is say, okay, well, what does that look like in terms of its spectral content? Because really, when you look at all detectors, they're really, what they care about is the spectral content that's there. Okay? So let's Fourier transform this thing. All right, so Fourier transforming is fairly easy. ut is FFT u. Okay, there it is. So I can say, all right, well, we're going to do some subplotting here. Subplot 2, 1, 1. We'll plot this. And subplot 2, 1, 2. We'll plot the Fourier transform. K versus, remember, actually, let's make this thing called Ks, which is the FFT shift of K. Remember, the K is FFT shifted, so is UT. So this is from last lecture. And then we'll plot the FFT shift of ut. And we'll plot the absolute value, because that's really all we care about. That's its power spectrum. Okay. Fourier transform pairs. Gaussian in time, or something Gaussian-looking-ish in time, is a Gaussian-looking thing in spectrum. Okay? Now, this is interesting, actually. Fourier transforms are quite interesting beasts. Associated with the Fourier transform is the Heisenberg uncertainty principle, which is there's a relationship between the width of the pulse in time and the width of the pulse in frequency. And the width in time and frequency is equal to 2 pi. Okay? So quantum mechanics was built on this idea that you can represent the state of a function or of the particle in terms of its probability density. And the Fourier transform of that represents its momentum. And so you can never know the momentum and the position exactly at the same time, because, in fact, there's this uncertainty relationship that the width of the momentum and the width of the location have to be equal to 2 pi. So all this is just inherent in Fourier transforms, and this is exactly what's happening here. So if I think about if I make this a really narrow signal in time, it's very broad in the spectrum, has lots of frequency content. If I make it very broad in time, it's like becomes almost a single frequency. Okay? So this is something about signals and Fourier transforms that you should know. Okay? Now, that's a side note. But here we go. We have the function, Fourier transform. And actually, you know, what I want to do is that we don't need to plot. I want to kind of blow up this region. So what I'm going to do, set the range there on the x variable so we don't have to see the whole thing. Axis, we're going to go from negative 25 to 25, 0 to 1. You know what I'm going to do here? I'm going to normalize this because divided by the max of this thing. So its maximum height is going to be 1. And then there we go. So then we can see it a little bit better because that's going to be important in a moment. Okay, so now what I'm going to do with this. Now what we really want to do is think about noise. Here is a really clean signal, and it's completely unrealistic. Because if I take a measurement, as I said, you have this whole bit of pollution going on in your spectrum. So ultimately, that's exactly it. What we want to think about is adding white noise to this signal. So what is white noise? So we usually think of white light as being a collection of all frequencies. So what I want to do is I want to go into the Fourier domain, which is its spectral content representation, and I want to add noise to every single frequency component. That's white noise. Okay? So how do I do that? All right, well, right there, see that ut equals FFT u? U of t is my representation now in frequency. And what I want to do is I want to add to every frequency component a little bit of noise. So let's call this UTN for the transform with noise. And what it is, it's this UT signal plus. What I need to do is add a little bit of noise. Let's have some noise coefficient in here. We're going to play with that. Check this out. Rand n plus I times rand n. And by the way, it's okay if you don't know all these MATLAB commands. You're just going to learn them over time. This is where you're supposed to be learning them. In other words, you're not like necessarily supposed to have known all this beforehand. So don't be all freaked out if you were getting freaked out there a moment ago. Okay, is everybody normal now? Okay, yeah. Heart pressure is okay. We should just have heart rate monitors on you guys, and it feeds it up right to my computer and go, whoa, there's a little spike right there. Okay, I'm just expecting that we're just going to learn everything you're going to need to learn about MATLAB, you'll just pick it up as we go along. We have all these demo notes in the lecture, or demo code in the lecture that you can just pick up and start playing with, okay? It's not like I'm saying you better know all this beforehand. There's a lot of stuff here that you're going to learn that I'm just, that's when you're supposed to learn it, here. Okay? But what this command does is does the following. So rand_n is a random normal variable. Okay? So it has mean 0, unit variance. So it's a random, normal distributed variable. Okay, so normally that's what we work with a lot of times, right? You want a random variable, then the one that you usually pick is a normal random variable, right? It's got some Gaussian distribution, probability distribution. We're just going to add noise to this thing. And we're going to add noise to every single frequency component. So what rand_n does is it makes a vector which is one row, n columns, and then it's going to add it to this vector ut, which is one row, n columns. So to every single component, it's going to add some noise. But what I've done here is added noise to both a real and complex part. If you only add real noise, it will be actually symmetric in the time domain. If you only add imaginary noise, it will be anti-symmetric. And there's reasons for that. We're not going to go into it. The point is, when you want to add white noise, add a real and imaginary part. So your noise has a phase at every single frequency component. It's different. And this parameter here, noise, is whatever I want to pick it to be.